Welcome everyone. We will be talking about product development and design from the point of view of manufacturing in this presentation. So everything to do with operation management as far as development and designing of product, keeping manufacturing industries at the helm. So this will be a little longish presentation. Probably I would love to finish it within 30 odd minutes. So basically what we are talking around here is design for X topic. Now X is for manufacturing, for production. X stands for anything. Assembly line, recycling. S for life cycle, prototyping. So design for manufacturing. These are the topics that we'll be covering out in this presentation. Or should I say, this is what the agenda would look like. Design for manufacturing, design for production, design for assembly, design for recycling or disposal, design for life cycle, and prototyping as the case might be. So gathering for design DFM is design for manufacturing information. So you will see a lot of DFM in this particular presentation. This is an abbreviation verb which I have utilized for depicting design for manufacturing or DFM information. So basically, what do we require for manufacturing? We require sketches, a blueprint, a product specification, expectation on design alternatives, and so on and so forth. And these sketches are basically nothing but a blueprint to what are the products that we are all planning to manufacture or develop in future. So a detailed understanding of the production and the assembly process which needs to be done, and it's the minute step-by-step manufacturing details need to be gathered around it. Estimating of the manufacturing cost, production volumes, and ramp up timing as the case might be. So if you look into it, this is a true pictographical representation of DFM method designed for manufacturing. We have the proposed design and see what is the acceptable design comes around it. Under this, there is a number of steps. Let's say we are looking at an estimated cost, manufacturing cost that we are talking about it. Can we reduce them? The foremost idea is, can we reduce the manufacturing cost in terms of component, in terms of assembly, in terms of supporting production? Now, how do we reduce it? We can manufacture it on our own if the scale is large enough, or we can outsource it, or we can give part productions manufacturing to some other vendors per se. In as a result, we overall reduce the complexity and the cost thereof. So consider the impact on DFM or design for manufacturing decisions on such thing. Should we outsource or should we manufacture, build it on our own scenarios, looking at the assembly part, looking at the component part, looking at the overall understanding of the manufacturing process. So then recompute this cost, and probably if you can arrive to a cost which is acceptable, you go for the acceptable design and go for manufacturing thereby. So design for manufacturing methods are estimating the manufacturing cost. There are basically five elements to it, five steps to it. First is the estimating or budgeting for it, and then looking for reducing the cost in terms of component, in terms of assembly line, in terms of supporting production. And then thereafter, we are going to consider the impact of DFM decisions on other factor, as in buy-in or outsourcing the material altogether. So let us understand in a pictographical representations, what are the estimates that we are looking into is that the manufacturing costs are out here. So basically, we're looking at equipment, we're looking at information and stooling. Now, these are the fixed material equipment machine that is required through which the manufacturing process will eventually take place. But what are the resources? Resources are your labor, your raw material, your component, purchase component that goes into the system. So once this two multiplies, now these has to be part of your manufacturing system. And then there is something called consumables, which has to be taken place in terms of energy, supplies, and services, which actually come up with the finished product. And then there might be byproducts also, which basically are considered waste. But if we can utilize those waste and convert it to a byproduct and probably to do anything out, make something which is of conducive use or sustainable utilizations for the company, nothing wrong in that altogether. So these are essentially the various manufacturing costs that has been involved around here. Remember, manufacturing cost is nothing but sum of all the expenses, all the expenditures for the system, for the inputs, for the consumables, be it component, energy, raw materials, and for the disposal of the waste that is being produced by the system altogether. So these are the manufacturing costs that needs to be taken into account. Remember, the waste that we are producing, it has to be disposed responsibly, and whatever the cost involved in disposing of it is to be accounted for. So, elements of manufacturing cost, we have the manufacturing in terms of component, we have standard and custom raw material processing tool. In terms of assembly, we have labor, we have equipment and tooling, and in terms of overhead, we have support and indirect allocation, as the case might be. So manufacturing cost of a product is the component cost, part of the product, part purchased from the supplier, custom parts made in the manufacturer's own plant or by supplier according to the manufacturing design and specification that needs to be understood time and again. We'll talk about the assembly cost is the labor, equipment, tooling cost that we are looking into it, overhead cost, all other costs that comes into the play is the support cost, material cost, handling, quality assurance, purchasing, and so on and so forth. These are your support costs, means these are your direct costs. Then what are the indirect overhead costs are not directly linked to a particular product but must be paid for to be in business. For example, responsibly disposing the waste in a responsible fashion, in an ecological fashion, so that it is not hampering the ecosystem in any fashion. So these are your manufacturing costs of your product. So we have a fixed cost and we have a variable cost. Fixed cost are the costs which are almost pre existing. Whether you are into manufacturing or whether you are not into manufacturing, you will have to bear the rent of the place, right? You will have to bear the capital that you are going to employ as deploy in terms of equipment that you are going to purchase and install. So regardless of the number of unit products, we need to have those costs. Let's say setting up the factory area, cost of an injection mold, so on and so forth. And now these are your fixed costs. You just cannot get immune to such costs. But what you can get immune to, or what are the costs which is flexible, that is known as variable cost incurred in a direct proportion to the number of unit produced. That is for the cost of raw materials is all about it. Now reduce the cost of component. Now what are the components that we are looking forward to? Understand the process constraint, cost drivers, redesign components to eliminate process step altogether. Choose appropriate economic scale for the part process, as the case might be. What I'm trying to do it, if we can change certain raw material, let's say in place of cotton, can we go for polyester material as such? Will it be durable? Will it serve the purpose? Can we reduce the weight of the equipment or the product by utilizing lighter, fluffier polyesters or polyethylene materials altogether instead of the hard raw steel or iron that can be taken into consideration. And you need to understand the appropriate economics of scales, how to eliminate the process, how to reduce the cost drivers, standardize component and processes, and believe me or not, adhere to the black box component. The black box is the blueprint that we have designed it at the very beginning of the project altogether, when we have decided upon what is to be done and what can be expected all under the roof. Understand the process constraint and the cost driver. Redesign costly parts with the same performance while avoiding high manufacturing costs. Work closely with design engineers, raise awareness of difficult operations and high costs thereby. These are the things that you need to go about as far as process constraint and cost drivers are to be taken into considerations. So redesign components to eliminate processing step. Now these are the component where we can eliminate either the component or reduce the component or the processes involved into it. So what do we do it? We can reduce the number of steps in the production processes. Now how do we can do it? We can sublet it to some other vendors. We can outsource it to some other vendors. Will usually result in reduced cost, definitely yes. Reduce complexity, definitely yes. Eliminate unnecessary steps. The moment unnecessary steps have been taken care of, it becomes much more simpler. Use substitution steps wherever applicable, analysis tool, process flowcharts, and value stream mapping. Then comes choosing appropriate economy scale as a part process. Economies of scale is production volume increases, manufacturing cost usually decreases. So if you are producing for in huge numbers, essentially it's spread that the variable cost becomes much more lesser and the fixed cost gets divided by the number of unit produced. If the large number of units have been produced, probably the cost per unit, the fixed cost per unit will actually reduce altogether. And as has been mentioned out there, so fixed cost gets reduced per unit. Variable costs are lower since firm can use a more efficient process altogether. Now we have standardized component and processes. The standardized component eliminates the fact that the same component can be utilized n numbers of time and anywhere. For example, your 3-pin plug, your power plug, if it can be standardized, we all know that the pin plug, the power plugs that we are utilizing for our laptops, for our mobile, are different in Europe, different in America, and different in Asia. Why so? If we can have a uniform process, we don't require those chargers any longer. A simple producer of charger which is unified and is being accessed, or should I say, can be uniformly manufactured at one place and acceptable round the globe. But that is not the case. So that is what the standardized component and process is all about it. So standardized component common to more than one product, as the case might be. As I've said about the chargers, analysis tools, group technology, and mass customization is what is the call for the day. Black box. What is a black box? Now, black box gives a description of what component has to do. It's your blue book. It is the holy grail that we are talking around it. Successful black box design requires clear definition of the function, interfaces, and interaction of each component, as the case might be. Reduce the cost of assembly. Design for assembly, DFA, as I said, of DFM, design for manufacturing. Integrated parts has its own advantages, has its own disadvantages. Maximize ease of assemblies and considers customers assembly line as the cost of the thing. So if we can have a standardized product, believe me or not, the assembly line becomes much more simpler. The cost can be further reduced or hammered down altogether, and this has its own pluses and minuses nevertheless. Now, design DFA, design for assembly line. No, what do we go around it for manufacturing and assembly? What has been present? We have the Boothroyd Duest methods, design for manufacturing and design for assembly line. Monroe and Associate, who talks about design for profit or profit, as the case might be, and the other system that comes around it. Yes, we are talking about the assembly index. Now, what is the design for assembly or DFA index goes about it? Theoretically, minimum number of parts multiplied by 3 seconds, because every part requires actually at least 3 times the seconds that we are looking into it, divided by the estimated total assembly time. And this is what the assembly uh, design for assembly will give up with the index part of it. What will the time delay, what is the cost delay around here? So determining theoretical minimum numbers of parts is, does the part needs to be relatively new, or can it be used in a multiple fashion to the rest of the assembly? Must be a part of the different material from the rest of the assembly, or fundamentally the same physical reasons? Does the part have to be separate from the assembly line and the assembly access, replacement, or repair? Example out here is for car manufacturing. In the assembly line, we have to take rubber into consideration. Why rubber? Somebody might ask. Rubber is utilized for tire purposes. Yes, the tire cannot be done in a steel industry where which the body part will be coming across, or the engine has been produced. So it has to be outsourced. Rubber can be always be utilized for your windshields and so on and so forth, to holding them out. So you need to understand it is the same material. How do we go around for it? Advantages of integrated parts: do not have to be assembled. They are part and parcel of the product altogether. Often less expensive to fabricate rather than the sum of each individual part that we look into it. Design critical geometric features to be controlled by part fabrication process versus similar assembly process, as the case might be. So we have the disadvantages. The disadvantages of integrated parts are conflict with other sound approaches to minimize cost. Not always, and I reassure, not always a wise strategy. So minimize ease of assembly. Part is inserted from the top of the assembly. Part is self-aligning. Part does not need to be oriented. It does not require for an assembly line. It has no tools. Part is more or less singular and a linear in motion secured immediately upon insertion. So consider customer assembly. Now there is certain thing which we can allow the customer to fabricate and assemble, be a part of the assemble process. Customer will tolerate some assembly on their own, design products so that customer can easily assemble a lot of products correctly. Customer can or will likely to ignore directions. These are things that goes around it. The question arises, show me an example where customer is a part of an assembly line. There are a lot of furnitures which is available online, or for that matter, I do not know whether the audience of this particular video have visited IKEA's furniture. IKEA's furnitures can be delivered at your home, and the customer, usually in American, the customer will usually take the directions which has been mentioned with the pamphlet, and they will read it and they will assemble it on their own, and it works very fine. It's very easy to do around it, provided you follow the step religiously. So reduce the cost of supporting production. This is where we minimize the systematic complexities as far as input, output, and transforming process is concerned. Use smart design decisions. We have the Pokayo or error proofing, anticipate assembly failures, possible failure nodes, take appropriate corrective actions in early stages, use color coding to easily determine similar looking but different parts. Consider the effect of design for manufacturing decisions on other factors in terms of time, in terms of development cost, product quality, external factors, and a part of external factors are component reuse and life cycle costs that we look into it. So design for production or DFP, what are we looking at in design for production? As far as manufacturing of in the industry is concerned, we need to understand the design organization, the timing of the production, the material identification, and specific details of the design. Thereby production input, what are they? We are to be giving designs right at the onset, at the conceptual part. As for the production input, functional, probably no or none units might be given. It is the output aeration would be the functional aspects. Transition is all about the tactics that we talk around it. Now in transition, you need to understand at certain thing, I'm sure you must have read about CPM or the critical path method. Certain elements can be done part A, part B, part C, part D, and it may not be singularly done. It can be done simultaneously. The only thing is part A and C can be done and fitted together. Part B can be integrated, and finally the part D gets as a cover to the product altogether. So yes, transition, you have to have your own tactics. You can go around it. You might have part D availability, the resources materials are available, so you go ahead with the manufacturing of part D, but A, B, and C have yet to be done. Or the resources material for one of the part is missing, so you go ahead with the same things, and probably it can be assimilated. So it is all about tactics. The transition is all about tactics. The work instruction is the production preparation that comes around. We need to understand those things. Now we'll talk about a new product or new idea as far as providing production inputs. What are the new ideas that can be incorporated right at the right to the proper level at the very initial stage, at every stage and initial stage, in a proper form and just in time methodology. The problems with old approach, what were they? They were basically too time consuming. There was a need for continuous recycling or reusage altogether. Work has been carried from beginning to end at each of the stage. We cannot simultaneously work on different part, as I said about A, B, C, and D. So you have to do part A, then followed it by part B, then it should be preceded by part C, and so on and so forth. This is one step at a time that goes around it. So this was the old approach. Now, what are we looking as DFP, design for production? The general principle is utilize common sense, plan and define, consider available facilities, consider available tools, consider available worker skills, enjoy simplicity and standardize as the case might be. So yes, we are talking of DFP. The guidelines thereby is to minimize the total number of part if possible. If it can be fabricated or it comes as prefabricated altogether, nothing wrong with it. So there are no questions of anomalies for fitting and for not so fitting, and probably breakages during the process of fitting and things like that. So develop a modular design, and that is the reason why we are the modular kitchen, the modular operation theater, the modular shop offices are so much in demand. Says minimize part variation, design parts to be multifunctional, design parts for multi-use, design part for ease of fabrication, and avoid, I repeat, avoid separate fastener. Similar guidelines continues as in minimize the assembly direction. It can be top-down directional preferred. Maximize compliance in assembly. Minimum handling in assembly. Minimize complexity of design. Maximize common jigs and fixtures. Optimize work position and ease of access as the case might be. So we'll talk about the last part of it. It's a type of prototypes. Approximately two-dimensional. There are prototypes which are physical, and there are prototypes which is analytical in your conceptual state, in your simulation products altogether. One once you can field out, and the other one is still in your laptop. Probably the computers have done the analytical parts about it. The other one would be comprehensive vis-a-vis focus. Comprehensive in totality, whereas focus in part, but completely in sync to that particular part, dedicated to that particular part. So two dimensions there are: physical versus analytical, comprehensive versus focused, as the case might be. Let me allow me to explain it further in this particular slide and the next slide. Physical is tangible artifacts, one which you can touch, see, feel, created to approximate the product, used for testing and experimentation. On the other hand, analytical will represent the product in non-tangible, usually mathematical manner. Did I say it is still there in a design phase in your laptop? Product is analyzed, but probably not been built. It can be simulated as far the utilization of the product goes around it, but still not been felt around. It's still intangible. Now let us understand with comprehensive vis-a-vis focused. Comprehensive is implementing all, in fact every attributes of the product. It is a full scale method, fully operational version of the product. Focused on the other hand is implement a few attributes to the product, use two or more focused prototypes together to investigate the overall performance of the product. Thereby prototype uses is learning, will it work, how well does it meet the customer needs, communication within the company with customer, vendors and suppliers, subsystems and component worker together, milestone, product achieve a desired level of functionality, as the case might be. Let us understand the principles of prototyping. Principles is analytical prototypes are generally more flexible than the physical prototypes is all about it. Analytical flexible is something which you are doing on a laptop probably, or it's still in the frame of the mind in the virtual space and the metaverse. Physical prototypes are required to detect unanticipated phenomena. A prototype may reduce the risk of costly iterations. Definitely yes. So it costly in terms of accident. Probably you can avoid accident, you can avoid huge investment in equipment and things like that. A prototype might expedite other development site altogether. A prototype may restructure task dependency, as the case might be. So use of comprehensive prototype, we have, on our x-axis we can have the cost of the component things. This is what we are looking at. It is the time, it is the money, less money, more money. Similarly on the y-axis is the market risk or the technical risk, less risk and more risk. So when the cost of money is low and the risk is also low, it is one prototype may be built for verification, nothing else. So probably it's a printed group. But when the cost is low and the risk is high, it is many comprehensive prototypes to be built and tested, time tested before going around it. So it can have a pilot survey, for example, software, consumer. Similarly, when a technical or market risk is very high, but the cost factor too is very high, then what we do, it has to be taken one step at a time. Analytical prototype has to be used extensively. Now what are the projects that might say market risk or technical risk is high and the cost is also very high? Probably if we are sending a satellite to moon, Mars, Venus, Jupiter, God knows for what, you see a lot of analytical prototype has to be utilized to understand what is going to eventually happen in reality. So it has to be a carefully monitored, carefully curated, comprehensive prototype. Sometimes the first unit built is actually sold. And I have said about the airplane, satellite and automobiles. But what happens when the cost is high, but the technical or market risk is absolutely zero or very low? It's few or no comprehensive prototypes are built. Probably you go ahead with it. And the commercial building and ships that we are looking out here. So 3D technologies is what the manufacturing thing is in vogue right now. We can easily visualize 3D forms of design, automatically compute physical properties other than focused description can be created based on one design, detect geometrical interference among part as the case out here comes around. So we have 3D prototypes now. We can have free form fabrication also, rapid prototyping as on when on basis. With the advent of 3D printers that create physical object directly into 3D computer models, it is absolutely very less expensive compared to the real projects, reduce product development times, and it improves the resulting product altogether. So planning for prototypes, remember, how do we go ahead with it? First and foremost, you need to understand or define the very purpose why are you going to build a prototype. Establish the level of approximations or your expectation of the prototype, the bare minimum and ecstatic expectation that needs to be clearly defined. Outline the experimental plan and create a schedule for procurement, construction, and testing the prototype altogether. Now, once you have built it around, once you have probably 3D printed or whatever things have been taken care of, once you then you do the pilot survey or pilot study altogether of your manufactured products. Now, is it performing to the level expected? If not, why? If yes, why? How good can you initiate the production, the construction, and the initiation of the product in the market, the launching of the product? So we need to define the purpose, list specific learning, specific communication goal, list all integrated needs, determine the prototype is intended to be one of the major milestone as the case might always say so. We can establish the level of approximation. Why? Because it's all about physical and analytical prototypes. You need to see the differentiation about what the analytical prototype was predicting and what has happened as an outcome of the physical prototype. Choose the simplest. I still recommend choose the simplest over complicated, over good looking prototypes. Choose the simplest prototype that will serve the purpose established in step number one, and consider using prototype or another prototype in build that can be borrowed, that has some sort of a precedence which can be built upon it. So outline the experimental plan, use prototype for experimentation, definitely yes. Extract the maximum value for prototype activity. Identify the variables of experiment, test protocol, plan for analyzing the resulting data. Then comes creating the schedule for procurement, construction, and test. Determine when parts are ready to be assembled. Determine the date when prototype will be first tested. Determine the expectation for the complete testing and final result as the case might tell it to you. Now, what are we looking at it? Milestone prototypes. Alpha prototypes are those prototypes where the product works as been predicted. Whatever we intended to produce, the product is actually doing it the same way. It is alpha prototype, the best one. Beta prototype, there are some anomalies, there are certain things which we are not very sure about it. So we need to identify those bugs and why the prototype is not working perfectly as per plan. So these are beta prototypes, and then we have the pre-production prototypes, the first product produced by the entire production process all together. With this, we come to an end of this presentation. I am sure you have understood the design for manufacturing of products only in this particular presentation. Remember, if you have understood this thing, your operation management scenario is getting much more easier to comprehend, and you will become an excellent operation managers in due course of time. Thank you for watching this video.